Okay, good luck. Thanks again, Mark. Hope to see you in the future in some other occasions.
Yes. I hope to visit Hungary again.
So I think the YouTube channel is on. We wait one more minute. Yes, okay. So thank you everyone for this Q webinar. This will be a very special occasion because today is the launching event of the World Quantum Day. So this year we celebrated it for the first time, but this will go on for also in 2022, 2023, and so on. And Q World is also involved in organizing this. And we decided to make a Q webinar with Mark Jackson, who is working for Cambridge Quantum Computing, and he will talk about the leading quantum development platform, tket. And the moderator, I will be one of the moderators, and János, who is actually an old friend of Mark, will be the other moderator. And this time, unusual for the Q webinars, we will end sharply at 5 p.m. or maybe even before, because at 5 p.m. Starts the main event of the World Quantum Day talk by Alan Aspe. Okay, so before we go on to introduce Mark, let me tell you a little bit about the code of conduct for Q webinars in general. I'm going to share that one. Yes, I hope. Does it work, this screen sharing? Yep. Yes, I think it works, thanks. So in the Q webinars and in all other Q World events, we are dedicated to providing harassment-free experience for everyone. So please don't write evil messages to each other. And we are recording this meeting and we will put online on our YouTube channel this talk. So please do not record or broadcast this meeting. Actually, this time, most of the people are watching it on YouTube, so you can watch it there, that we are broadcasting. And we will also actually put on our website and on our Facebook channel the availability on YouTube when it's done. And also here in this the Zoom channel and also in the YouTube channel, you can ask questions. There is a chat on the YouTube channel. I will be watching them, and also János will be watching them. And we will ask basically after the talk, Mark, about this. So that should be the code of conduct that we should follow in the protocol. And finally, I will put up the bio of Mark, but I will actually give the word to János after that.
So Bár Zoltán is putting up the bio. Today's speaker is Mark Jackson. Mark is a physicist by training. He obtained his PhD at Columbia University in 2004. He worked with the famous Brian Greene of string theory. So his PhD thesis was on brane gas cosmology in superstring theory. And he continued theoretical research career in string cosmology. And that's how I met him in Leiden in 2008 or 9, where he was a postdoc and I was a postdoc as well. And after a few more years working as a string theorist, Mark saw the light and decided that that he would turn towards quantum computing, and he's now working for Cambridge Quantum Computing. He is working for Cambridge Quantum Computing since 2017, first as a scientific lead of business development, but recently his job title changed, and now he's a quantum evangelist. So we are very much looking forward to what you have to say to us, Mark. Thank you very much for accepting to talk.
Sure. So thank you, Zoltan, and thank you, Janos. It's a real pleasure to be here speaking to you, especially on World Quantum Day. It's a very exciting time, and it's an honor to be speaking to you. I'm sorry that it's only online and that I couldn't actually visit you in person. As Janos mentioned, he and I were actually postdocs back in Leiden in Holland in 2008 to 2009. And a few years later, he very kindly invited me to visit Budapest. And in fact, I even managed to find a few photos from those days.
Great, that's great that you brought those.
this was the trip. So we had a very good time, and I hope that once circumstances allow that I'll be able to visit again. I very much enjoyed my visit. Today I'll be telling you about tket, which is the leading quantum development platform. So tket is at the simplest level, it's a quantum compiler, and I'll explain more about what that is, but it's actually much more than that. And this was developed by the company I work for, Cambridge Quantum Computing. And I want to take just a minute to say a few words about CQC. We were established in 2014, which actually makes us one of the oldest quantum computing companies that exists now. And we now have about 140 people, and we're growing very rapidly. So that also makes us one of the largest quantum computing companies. We have a very interesting origin story. Our founder and CEO, Elias Kahn, was actually chairman of the Stephen Hawking Foundation. And it was Stephen Hawking who told him in 2014 that quantum computing was going to take off and he should get into this business. And so we're very fortunate that Stephen Hawking made this observation back then, because it certainly proved to be correct. We develop quantum software. We don't build the actual machines, but we have close relationships with every major quantum hardware provider like IBM, Google, Honeywell, Microsoft, etc. And we're especially close with IBM and Honeywell. They're investors in ours, and we have the ability to resell time on IBM and can connect you with time on the Honeywell devices. And I'll say a little bit more about that later. We have expertise in every area of quantum software. So I'll be focusing especially on the tket compiler today, but we also have expertise in quantum chemistry and machine learning and cybersecurity. And I'm sure in the other seminars in Quantum Hungary and Quantum World that you'll be hearing a lot more about those. I think most people watching this presentation already have some familiarity with quantum computing and what it is, but let me just very quickly summarize it in case you don't. Normal computers work with bits, which are just ones and zeros, and you can think of that a bit like heads or tails on a coin. It's exclusively one or the other. Quantum computers, on the other hand, work with quantum bits, or qubits, which can be a 0 and a 1 at the same time. And the technical name for that is superposition. And it's a bit like, to use the coin analogy again, it's like the coin is flipping in space. It's sort of in between the 0 and 1, or heads or tails state. And when you combine that with another concept called entanglement, which means that these qubits can have values which correlate with other qubits, even if they're separated by a far distance, then that gives rise to very powerful computational tools. And we believe that quantum computers could solve problems that we never could have hoped to have solved before. And a classic example is in chemistry. This was actually one of the first reasons that quantum computers were developed. It was Richard Feynman who suggested about 40 years ago that normal computers would never be able to solve these types of chemistry problems, because as the molecule gets bigger and you have more atoms, every atom has more electrons, and the electrons all interact with each other. And so the problem quickly becomes intractable for a normal computer. If you just look at the scaling, it means all but the very simplest molecules would be impossible on a normal computer. Just to take the example of caffeine with 24 atoms, you would need about 1 to 10% of the Earth's atoms. You need that big of a computer to analyze that problem. And for a bigger molecule, penicillin with 41 atoms, you would need the entire universe. And so clearly, even theoretically, you wouldn't be able to come up with a computer bigger than that. On the other hand, quantum computers could very, I wouldn't say easily, but could very reasonably tackle these types of problems. And so that's why people are so excited about quantum computing, because we believe they could solve problems that we never could have hoped to have solved with normal computers. They really exist. This is not science fiction buzzword fantasy. Quantum computers now really exist, and there's many different approaches to building them. So there's lots of different technologies that are being employed to build quantum computers. A very popular approach is superconducting, which is an approach used by IBM and Google and Rigetti and others. Another approach is the ion trap method, employed by IonQ and Honeywell and others. And then there's photonic and a few others. And these are all promising, and I truly don't know which the winner will be. There will probably be several winners because different approaches are better suited for different types of problems in quantum computing. It's not just the number of qubits that's important, and this has been more thoroughly realized in the past few years. There's now another metric which is being employed by some, especially IBM, called the quantum volume. And so the quantum volume is one metric which takes into account several aspects, including the qubit quality. And so, for example, this is how you calculate it. It's sort of calculated on a logarithmic or exponential scale. And so this is really the kind of the one metric. If you had to estimate the power of a quantum computer, this is kind of the single number that you can rely upon. And if you look at this chart showing the progress of quantum computers over the past several years, it's really impressive. Many of you are probably familiar with Moore's law, which has shown that classical computers have doubled in power every 18 months or so. And that has held true for several decades. What's maybe less well known is that quantum computers have been on an even faster trajectory. If you look at the quantum volume over the past few years, this blue line shows the progress made by IBM, and you see that they've actually more than doubled the quantum volume every 12 months. So that's even faster than Moore's law. The orange line shows the progress made by Honeywell, and it's quite a bit faster than that. They actually believe that they could increase the quantum volume by a factor of 10 every year for the next 5 years. And the past year or two has actually held that true. And so just recently, they've had a quantum volume of 512. That yellow dot up on top is by IonQ, and again, they use the ion trap method. They claimed a few months ago that they will soon unveil a quantum platform with a quantum volume of 4 million. And that's incredible if true, of course. That's several years ahead of where the others would be. I have no reason to doubt that. I only put an asterisk there because it hasn't been confirmed by other independent sources. But IonQ is a fantastic group, and so that I'm really looking forward to that. So I just wanted to convey how rapid the progress has been in quantum hardware, and that this is a very aggressive timescale. Both IBM and Google believe that they'll have about 1,000 qubits within 3 years, and they have a roadmap for 1 million qubits within 10 years. And so in the next few years, we really should see some incredible progress. We're not there yet, unfortunately. Right now, we do have quantum computers, but it's in what's called the NISQ era, the noisy intermediate scale quantum. And what that means is that we have quantum computers, but they're not yet the dream machines that we kind of anticipate in the next few years. We have about 50 to 100-ish qubits. There's still relatively high error rates, and there's no way that we can do error correction. So error correction is a way of kind of spreading the information in one qubit among several qubits, so that if one qubit fails, the others can kind of recover and make up for that. The thing with error correction is that you need a pretty small error rate to begin with. Otherwise, doing error correction actually makes the problem worse, because by adding more qubits, you're making it more likely that something will go wrong. So you need the error rate to be pretty small for error correction to even work at all, and we're not quite there yet. And so right now, we actually just have to take the qubits as they are, again, 50 to 100-ish qubits. And so that means that we have to keep the circuits pretty small. The quantum programs or circuits, we have to just run them and hope for the best. So that means that a lot of approaches are using what's called the hybrid approach, where a lot of the heavy lifting is done by the classical computer, and only a small amount of work is done by the quantum computer. Only the commands that most benefit from running on a quantum computer are sent to the quantum processor. And so this quantum and classical hybrid approach is proving to be very popular. So I'm mentioning all this for a reason. I really want to emphasize that right now we have a lot of constraints on the types of problems that we can run. Many of you probably have enough computer experience that you know what a compiler is. So when you, as the human programmer, when you write a computer program, you typically write in a program that's understandable to you, like Python or C or what have you. And even though it looks computer-ish, it's still understandable to humans. Machines understand something completely different. It's really just binary data that instructs the machine on what to do. And so you need a compiler to translate between those. And a good compiler doesn't just translate what you write as the human programmer into instructions for the machine. It also makes it efficient because you want the programs to run fast and to use as little memory as possible. And so this is very common. This is very well known for normal computers. It's identical for quantum computers. We still need a compiler for that. And so that's what I'll be talking about today. So anyone using a quantum computer has some sort of problem that they want to solve. And so that's on the very top of the stack. And to do that, they'll be using different algorithms like chemistry or machine learning or natural language processing or what have you. So there's all these algorithms which are written in Python or C or some quantum specific language like tket or circ or what have you. All of that will sit on a compiler. And what I'll be talking about today is the tket compiler developed by Cambridge Quantum. The tket compiler interfaces between you as the programmer and the hardware. And you notice I've included several names there for the type of processor, and that's because we have a lot of different platforms right now. There's a lot of different approaches to building quantum computers. This is kind of a schematic of what it is. So again, on the left-hand side, there's a few different programming languages like tket and Q# and circ and what have you. And then on the right-hand side, there's all these different platforms. And I mentioned a few minutes ago, it's not just that these are built by different companies, they employ very different technologies. And all of the ones that I've mentioned here have one thing in common. They're all gate-based machines. So they all have the basic idea that you have different qubits, which are first initialized, and then they're manipulated. We apply gates to them to change the value of the qubit, sometimes depending on the value of other qubits. And at the end, we measure them. And so then we just recover the normal binary data. So they have that basic feature in common, but the specifics of how you manipulate the quantum computer is very different. And I'll say more about that in a moment. But I really want to emphasize that, yeah, tket sits between you as the programmer and all these different quantum platforms. Now, this idea of a universal compiler is actually kind of unique to tket. If you use one of the other programming languages or one of the other cloud platforms like Azure or AWS bracket, you're pretty much locked into using one or maybe just a few quantum platforms. And the reason that we developed tket is because we wanted one compiler which works on all of them. And you see a comparison here of tket compared to some of the others. Tket allows you to have nearly universal access to any quantum platform. The only two missing here are D-Wave, because that's a quantum annealing platform. So it's a completely different approach to quantum computing. And Quantum Circuits Inc. We don't yet support it, but we're looking into that for the future. Every other major quantum platform is supported and several minor platforms are supported. And I really want to emphasize that you simply type your program in, and in one line of your code, you indicate which platform you want to use. And then you execute it. Tket will automatically compile your program in the most efficient way possible for that platform that you've chosen. If you change your platform, say you move from you want to use the Google machine instead of the IBM machine, you simply change that one line. You don't need to completely rewrite your program, and you don't need to be aware of all of the idiosyncrasies of how the qubits are coupled and the topology and everything like that. Tket knows all of that for you. So you just focus on writing your code and let tket do the rest. What does it mean to efficiently compile? How does that really happen in practice? So there's actually two halves to the story of efficient compilation. So the first half of that is making the circuit itself most efficient. And so, so you've probably seen in quantum programs, it looks like a bit like a musical score. You have the qubits initialized, and then you have these gate operations, and then the measurement. You would like to make this circuit as small as possible. And this has nothing to do with the hardware that you're going to run it on. This is just the abstract theoretical circuit itself. And so what tket does first is it takes that circuit and it looks for small, what are called peephole ways to make it more efficient. So it looks at local features at the individual gates and the surrounding gates, and it looks for patterns that it recognizes that it can simplify. So for example, if you have two Hadamard gates in a row, that's mathematically equivalent to just the unity operator, which is nothing, no operation itself at all. And so, so by doing little things like this, by looking for local patterns that it can simplify, tket first simplifies your circuit. The second thing it does here is more macroscopic. So it looks for more general ways that it can simplify your circuit. And this is a little bit more sophisticated. And so we've employed many mathematicians to come up with mathematically sophisticated techniques to optimize this. The second thing that it does is, once it has the simplified quantum circuit, it needs to execute that on the quantum hardware that you've chosen, such as Honeywell or IBM or Google or what have you. And this very much depends on the way that the qubits are physically adjoining. And so tket is aware of that. It's aware of how the qubits are connected. And so it has to come up with some sort of map of how your circuit, your theoretical abstract circuit, will map on to the physical qubits that you actually want to run this on. And so this is it's a very difficult mathematical problem, but tket does a good job of doing this. And so it looks for the most efficient way to map it onto the platform that you've chosen. And to give you just a small example, these are a few of the superconducting platforms. So again, these are all gate-based approaches, and these are all superconducting approaches, but these are by 3 different companies. These are 3 different platforms. And you see that the connectivity between the qubits is very different. The way that the qubits are physically adjoining and therefore interact is very different depending on which platform you're using. And even more than that, the gates that are native to that machine are very different. And so, so at the bottom of the screen here, I've given a few. So these are the gates that the platform understands, no others. And so when you write your program, you may not be using those gates necessarily. You'll probably be using others. So tket will also automatically do the translation from whatever gates you've used into the basis gates, which the platform actually understands. So again, all of this is invisible to you as the user. I'm just highlighting how different it is by switching platforms and how much work is required kind of underneath the covers there. So this is how it does the routing, how it actually maps your theoretical circuit onto the physical device. And this is a very difficult problem. It's actually NP hard, but tket has done a really good job of doing this. It is not just CQC using tket for our own internal algorithm development. A number of other groups have been using it. We have thousands of users now. So, so IBM has been using it, CERN has been using it, and these headlines here are just a few of the articles that have been written of people using it. We very much encourage you to use it. Of course, we're very concerned with how it compares to other compilers. So there was a great benchmarking study done recently by Arlene, and these are 2 of the results that they found. So on the left-hand side, this is a comparison of the number of gates that the compiled program had using tket compared to a few of the others, and it compared favorably. On the right-hand side, this is a graph of the execution time. And I want to draw special attention to the vertical axis. You notice that's actually logarithmic. And so you notice that tket was actually orders of magnitude faster in executing programs than some of the other compilers. And so it really is a dramatic difference. And I went into detail about today's NISQ era because I wanted to emphasize that right now, having an efficient program could mean the difference between running a program and not running it. If your program takes so long to run and it uses so many operations, you may not be able to run it on today's machines. And so it's really, really important that you have your program be as efficiently compiled as possible. Again, on the right-hand side, these are the URLs if you'd like to look up the benchmark and study yourself. We're constantly updating it. We're now on a monthly cadence of updates, and we're now up to version 0.9, I believe. The major change that we made just about 2 months ago is that we have removed all licensing restrictions from tket. And so, so you're welcome to download it and use it right now. And there's no fees, there's no licensing terms, there's absolutely nothing. So we just want the world to use this and benefit from it. We only ask that if you use it and you write an article, please just credit that you use tket and give us feedback on how we can make it better, because we're very interested in how people are using it at a practical level and how we can improve it. Again, we're constantly updating it to include the latest quantum hardware. So, so if a company like IBM unveils a new quantum platform, we will incorporate that support in the next update. So, so we always have the latest quantum platform supported. This is how you can download it. There's a GitHub repo, and I'll leave this up here for a second in case you want to take a screenshot to look it up later. So there's a repo with all the instructions and documentation and examples, and so it's very standard. This is the PyTicket repo, so you can use Python to use this. And the installation is completely straightforward. You just use pip install, not only for PyTicket, but also for any hardware platform that you think you might want to use. So you don't need to install modules for everything under the sun, just the few that you expect to use. And of course, you can always add more later. And so that's it. Everything is ready to go after that. So yeah, I just want to make one final mention. For those of you who probably don't have million-dollar budgets for your quantum computing research, to actually access quantum hardware, it's pretty expensive right now. IBM very kindly has a free online quantum platform, the IBM Q Experience, for their lower end machines, like 5 qubits. But if you want to use the higher end premium devices, like 50 to 100 qubits, you typically have to get a multi-year contract, which can cost a few $1 million. And especially for academics or startups, that's clearly not feasible. I just want to mention that we are authorized to resell time on IBM's devices in increments of 6 months, and you would be sharing it with only a few people. And so this is quite a bit better than IBM directly, and we can introduce you to Honeywell's team if you'd like to discuss access with them. So, so yeah, so I just want to emphasize that it's becoming more accessible to actually use real quantum hardware instead of just simulators. So that was it for my prepared remarks, but I'm happy to stick around and answer any questions that you might have.
Thank you very much for this very nice presentation, Mark. So there are already a couple of questions here and on the YouTube channel. So maybe let's first begin with the questions there. There's a generic question in the YouTube channel, the CQCs on the stock market. I guess it was inspired by the fact that IonQ has now this publicly traded stocks. I don't know if what you can say about that. I mean, it's less of a scientific question, but still.
Sure. I have nothing to add. It is true, as you say, IonQ has announced they intend to go public. I'm not aware of any plans to go public or anything, but I'm not on that side of the company, so I wouldn't know. So
okay, thanks. So one question from the Zoom was that I mean, you talked a lot about compiling quantum circuits into elementary gates, native gates. So the question is, can you use, or maybe can tket use machine learning techniques for better compilation of quantum circuits? Do you have any?
Yeah. So that's a very good idea. That's exactly what we do. We actually do use machine learning for this, because at the heart, it is an optimization problem. You're trying to find the most efficient way to execute the program and minimize the number of gates and minimize the time taken, subject to these constraints. I'm not on the scientific team that writes tket, so I can't be more specific. I know that it's based on the mathematics called ZX calculus or ZX calculus, which was actually developed by Ross Duncan, who's head of tket, Bob Cook at Oxford, who now works for us. And so it is based on very mathematical machine learning techniques.
Okay, thanks a lot. So there are two more questions on the YouTube channel. One you already answered, whether tket is open source. So yes, and you also showed how you can download it. And
let me just clarify. It's not.
Okay.
It's not open source.
Not open source. You are right. It's just free.
It's freely available without licensing. Exactly. So you don't.
I see. Okay,
anything.
thanks for this.
But the code itself is still proprietary. Maybe at some point that will change, but at least today it's not.
Okay, that was actually a great clarification. And the final question there was actually from Tony Apollaro, who is one of the main organizers of the World Quantum Day beside Yasser Omar. And he asked whether tket supports fermion to qubit mapping, for example, a Jordan-Kitaev type of transformation, or the Bravi-Kitaev transformation, and other type of things. So if it's built in or so on, whether you can simulate easily fermions with, let's say, qubits.
Sure. So this is a very typical problem in chemistry, I believe.
Yes.
Where qubits represent fermions, or the electrons specifically. So yes, we certainly do that in our chemistry applications. And so I don't know if that's a native feature of tket, because tket really just takes the circuit that you've written for qubits and finds a more efficient way to do that. So whatever those qubits are representing, that's up to you. I don't think tket's aware of what it's physically representing, but yes, it's certain that is something that you can do.
Okay, thanks a lot. And then we got actually a new question here. I really like it in the Zoom by one of the main pillars of Q Hungary, András Pályi. He says that maybe this is a provocative / naive question, but I'm really interested how and when will CQC generate income?
That's a good question. So yes, if we're giving tket away for free, how do we generate income? The way that we generate income is because we develop quantum applications like chemistry and machine learning type projects. And we have industrial clients which hire us to do that. And we're a little bit different from other quantum companies. Most others are consulting. So they'll do a report or maybe design an algorithm or something and then hand it to the company. We don't do that. We build applications. We keep the intellectual property for the quantum side of it. So the application is ours, but we license the results to companies if they're interested in some result. So like if you're a material science company and you want to know the chemical properties of something, we'll write a quantum application which will be able to determine these properties of this molecule, and we will allow you to use those results for some amount of time for some purpose. And so we get paid to develop these applications. So that's how we generate income.
Thanks. And then there is a final question. Let me read this. It was okay. It's a very part. I don't know if you can answer it. So the question is from Akash Kundu, who I actually know very well. So if you implement a big circuit and suppose that at one instant there are two Hadamard comes consecutively, like after each other, which would be like a unity, then is the depth 1 or 2 in tket? I don't know if you can. I guess it's a good question. I don't know if maybe it's a very particular question, right?
Sure. So let me answer what I think you're asking. So the naive circuit, which has two Hadamard gates in a row, so
exactly.
It would seem to have depth 2, but tket can simplify that. It removes them both, so it has depth 0 because you don't need to do anything after that. So that's what tket does, is it simplifies and lowers the depth.
Okay, thanks a lot. So I also have a question, and then I maybe ask János whether he has. So my question was that you said that you can have, if we can come to you for perhaps if we want to run some interesting circuit on a bigger IBM machine that is not reachable online, like openly. And so is it, so how does, first of all, how does this work exactly? And my second question about the Honeywell. So for the Honeywell, is it similar that can we come to you and buy, let's say, machine time for Honeywell? Because you were like a little bit saying that maybe you can introduce us to Honeywell. So I was unsure about that because many people are interested in running the Honeywell machine.
Yeah. So with IBM, again, this is only because of a special relationship, because they're investors in us, and so we have a close relationship. With IBM, we are an IBM Quantum Hub. That's the formal name for that. And so we can resell access to the premium devices in increments of 6 months. You would share with 3 other groups, and CQC would be one of those groups. And so we would work on a project together, but it's very, very flexible what that project could be. So it could just be like training or benchmarking or something. So it's very flexible, and we could accommodate whatever your project is. For the Honeywell, we're not authorized to resell it ourselves, but we can connect you with that team at Honeywell that does that. And so you don't need to try to figure out who's who and get an introduction or something. We will make the introductions. You will go right to the top of the line and discuss that and negotiate it with them privately.
Thank you very much. So Janos, do you have some questions?
Sure, but maybe I first read 2 more questions from YouTube, which have since popped up. One is from Francesco Scala. Does tket have libraries about quantum machine learning, quantum chemistry, etc.?
Yes, there are some libraries, and it also takes advantage of Qiskit. So you can program in Qiskit, the IBM language, and just use tket to compile it. So all the libraries from Qiskit and such immediately move over to tket.
Emil Dimitrov is asking you, could you give us a quick comparison of tket versus PennyLane? There seems to be a lot of overlap in the scope between those 2 Q compilers.
Yeah, so PennyLane is developed by a company called Xanadu in Toronto. So Xanadu is developing photonic quantum computers, and they're developing software like called PennyLane to use it. There is some overlap, and PennyLane's an excellent product, which is why the latest version of tket supports PennyLane. So you actually don't have to choose between them. You can actually use both.
Okay, thanks. Utku Birkan is a ZX calculus aficionado. He says, I saw the PyZX extension for tket in the presentation, and he was recently tinkering with ZX calculus, enjoying the notation. How does tket perform with quantum circuits versus ZX diagrams?
I wouldn't be able to answer that. That's over my pay grade. What you can do is maybe I can put into the, I'm going to put into the chat here, tket support at cambridgequantum.com. And so if you have any technical questions about tket or ZX calculus or something, the tket team is happy to answer those questions.
Okay, I have relayed this information into the YouTube chat.
Exactly, thanks.
And so my question would be, you flashed us a slide of some examples where people have used Cambridge Quantum Computing's expertise. And could you give us a little more insight, maybe some industrial example which you are allowed to talk about? It's already done,
Sure.
and you're proud of.
Sure. So I can give you a few examples of projects that we've worked on. And
Yep.
as Jana correctly said, we don't talk about all of them. It depends on what the client wants. So some of them want us to promote it, and we issue press announcements and everything. And others, we can't say anything at all. And so, so yeah, I can mention a few. So we have a few financial clients that we've been developing quantum machine learning algorithms for, particularly with quantum Monte Carlo algorithms. And some of you might be familiar with Monte Carlo programs where in a lot of problems, there's some sort of randomness, like in a stock market where you don't know what's going to happen. And so you have to simulate it many times using random numbers, and you try to you try to anticipate what the expectation value of some value is, like the value of a stock. And the more times you simulate, the more accurate a result you expect. The convergence is with square root of n. So the more times you run it, the more accurate, but it's kind of diminishing returns on that. It's square root of n is just like a Gaussian spread. With quantum Monte Carlo, it's actually just n linearly. And so that's quite impressive. That's like getting the same level of accuracy using a quantum computer with 1,000 simulations as with a normal computer with 1,000,000, because 1,000 squared is 1,000,000. And so so we've been developing many things along that direction. In chemistry, we've done projects involving carbon capture to try to reduce the amount of carbon in the air and such. Simple chemistry, like photoabsorption type values in molecules and such. Let's see, we just signed an agreement with Crown Bio and JSR Life Sciences for genetic data. When you're looking at the correlation between genes, when you're looking at linear correlations, you can do that on a normal computer right now. When you're looking at quadratic correlations, you can kind of barely do it with a normal computer, but it would be impossible to do cubic interactions, because that's like 20,000 squared. If there's 20,000 genes, there's just no way you can do it. And so we're looking at ways that you could use a quantum computer to speed that up. And so the idea is that you can look for how effective different drugs are based on someone's genetic makeup. And so these are some of the first steps towards developing personalized medicine.
That's funny. It reminded me of our time in Leiden. I think you looked at correlations in the cosmic microwave background.
I did.
Data?
That's true. I hadn't made that correlation, but yes, that's true.
So maybe you could use Cambridge Quantum Computing's access to quantum computers to.
I'm sure that, yeah, someone will develop a quantum algorithm for looking at the correlations in the CMB data.
Thank you very much for all the answers. So actually, everybody, thank you also in the YouTube stream. It was a great talk, and it was a little bit shorter event than usual, but the reason for this is also that, which I also invite everyone, is that Alana Spey is also going to give the main talk of the World Quantum Day soon at 5 p.m. and everybody can find it on the worldquantumday.org. So thanks a lot, Mark, for this very interesting presentation, and I hope that you will be able to come to Budapest soon, visit János and us.
Thank you again, János and Zoltan, for arranging this, and thank you for attending, and I definitely hope to see you all in person soon.